In this video, we are going to be talking about algebra and composition with functions. So if we are given two functions, f of x and g of x, we can define four new functions as follows. So we have the sum f plus g of x, which is just going to equal f of x plus g of x. We have the difference f minus g of x, which is just going to equal f of x minus g of x. Then we have the product f times g of x, which is just going to equal f of x times g of x. And then we have the quotient f over g of x, which is just equal to f of x over g of x. All right, let's get into our examples. So in these examples, we are going to let f of x equal x plus 1 and g of x equal to 2x minus 3 and h of x is equal to x squared. Okay, and we want to find the following. So in example I, we are just asked to find f minus g of x. So according to the properties of functions above, well, this is just going to equal f of x minus g of x. And so now we can actually replace these guys with their formulas. So f of x is just, again, x plus 1, and then minus, and then all in parentheses, the formula for g of x, 2x minus 3. All right, and now we can drop the parentheses and add like terms. Also distribute this minus over both terms in the parentheses. So let's see. I don't think we'll run out of vertical space, but I'm a little worried. So we have x plus 1 minus 2x, and minus minus, so plus 3. So x minus 2x is going to be minus x, and then we have 1 plus 3 is 4. F minus g of x is just equal to minus x plus 4. All right, now for example 2, we want to find f plus g minus h of negative 2. So, you might be worried because it's like, well, what should we do here? These rules are only talking about one function, and we have three functions in here. Well, we can always think about just kind of breaking things down. So we can first say, all right, we have f plus g minus h of negative 2, which according to the sum rule, or the sum property, we can rewrite as f of negative 2 plus g minus h of negative 2. And then we can use the difference property to say, okay, this is equal to f of negative 2 plus g of negative 2 minus h of negative 2. Okay, and then from here we can see that we are going to have to figure out what f of negative 2 is, what g of negative 2 is, and what h of negative 2 is. So let's go and figure out what those are going to be equal to first. And then we'll worry about coming to our final answer. So f of negative 2 well, this is going to be equal to negative 2 plus 1. Which is equal to negative 1. And g of negative 2, well, this is equal to 2 times negative 2 in parentheses, and then minus 3. And so we're going to have 2 times negative 2, which is negative 4, minus 3 is equal to negative 7. All right, and then we want to find h of negative 2. And this is going to be equal to negative 2 in parentheses and then squared. We want to make sure that negative 2 is in the parentheses because otherwise we might forget to square the minus out in front too, which would cause us to write a negative 4 instead of correctly writing a positive 4 for h of negative 2. All right, so that's the value of h of negative 2. So let's go and plug all this in. So we have f of negative 2 is minus 1 now. And then we have g of negative 2 is minus 7. And then we have h of negative 2 is 4, so that's going to be a minus 4. So we have minus 1, minus 7, minus 4, which is going to be equal to minus 12. Whoa, it's a little too thick. All right, we have two more of these examples. So in example 3, we are asked to find g times h minus f of 1. So again, we're going to kind of break this down with the different properties like we did in the previous example where we had more than one function to deal with, or more than two functions rather. So all right. So g times h minus f of 1, well, this is going to be equal to, according to the difference property, g times h of 1 minus f of 1. And then according to the product property, we can say that this is equal to g of 1 times h of 1 minus f of 1. All right. Now we can see that we want to figure out what g of 1, h of 1, and f of 1 are. So let's go off to the side and calculate those values really quick. So f of 1 is going to be equal to 1 plus 1, which is just going to be 2. G of 1 is going to be equal to 2, and then parentheses, put the 1 in there, minus 3. So we have 2 times 1 is 2, and then minus 3 is going to be minus 1. And then we have h of 1, which is just going to be equal to 1 squared, which is equal to 1. All right, so let's go and plug all that in. So we are going to have minus 1 g of 1 times 1, and then minus 2. So this is equal to minus 1 minus 2, which is equal to minus 3. All right, now we have our fourth example, and we want to find f over g of 3. So we are going to use the quotient property here, and we are going to say that this is equal to f of 3 over g of 3. So let's quickly figure out what f of 3 and g of 3 are to write our final answer here. So f of 3 is going to be equal to, well, 3 plus 1, which is going to be equal to 4. And g of 3 is going to be equal to 2 parentheses 3 in there, and then minus 3. So we have 2 times 3 is 6, minus 3 is 3. So f over g of 3 is equal to 4 over 3. All right, now let's talk about composite functions. So given two functions f of x and g of x, we defined the composite f of g of x to be just equal to f with g of x inside of it. And so let's get into our examples here. So in these examples, it says let f of x equal x minus 3 and let g of x equal x plus 2 squared. And we want to find the following. So in the first example I here, we want to find f of g of x. So the composite of f composed with g. So let's see what that is. So according to the definition, well, this is just going to be f of x with g of x inside of it. So. And now we can go ahead and replace g of x with its formula. So x plus 2 squared, or rather its rule of assignment. So this is going to be equal to f of, and then in parentheses, we're going to put x plus 2 squared. So it's like instead of having x as the input, we have x plus 2 squared as the input. Or in other words, to find the composite, we have to evaluate f at x plus 2 squared. So now using the rule of assignment for f, this is going to be equal to x plus 2 squared minus 3. And just by the way, so x plus 2 squared, foiling this out, is equal to x squared plus, so that's first times first, and then outer times outer, we'd have x and then times 2, so 2x, and then for inner times inner, we'd have 2 and then times x, so plus 2x. And then for last times last, we'd have 2 times 2, so plus 4. So this is equal to x squared plus 4x plus 4. And again, we expand this binomial according to the FOIL acronym. We multiply the first terms, then we multiply the outer terms, then we multiply the 2 inner terms, and then we multiply the 2 last terms. Right? All right, on to example 2. So now we want to find, returning to example 1, the reason why we FOILed out x plus 2 squared is in case we want to simplify what we have here. So seeing how we could add like terms. So considering what x plus 2 squared is, this is going to be equal to x squared plus 4x plus 4 minus 3, which is equal to x squared plus 4x, and then adding the like terms plus 1. Okay. In the Lumen problems, it doesn't matter if you simplify your expression for like the composite function. So we could have left our answer as x plus 2 squared minus 3, or we could have simplified it. Lumen will count it correct either way. All right, so now let's move on to example 2, where we want to find f of g of 1. So since we already know the rule of assignment for f of g of x, we could use that to evaluate f of g of 1 by just plugging in 1 and for x into what we found in the previous example. So if we were to do that, it would look like, well, one squared plus 4 times 1 and then plus 1, which is equal to 1 plus 4 plus 1. Which is equal to 6. Or we could find g of 1 and then evaluate f at g of 1, whatever that is. So we could say, all right, f composed with g evaluated at 1 is going to equal f of g of 1. So let's figure out what g of 1 is. So switch over to, well, actually, I'm going to leave it purple. So g of 1, well, that's going to equal 1 plus 2 squared, which equals 3 squared, which equals 9. And so this is equal to f of 9 now, since g of 1 is 9. And so now we just have to evaluate f at 9. So that's going to be equal to, according to the rule of assignment for f, 9 minus 3, which is also 6. I'll write it over here. So either way, we arrive at the same answer. And you can do these problems where you're actually having to evaluate the composite at a specific value in either way that you prefer. All right, we have 2 more of these examples. So in example 3 now, we want to find g composed with f. So this is just going to equal g with f of x inside of it. And so we can replace f here with its rule of assignment. So this is equal to g of, and then x minus 3. And so we essentially want to evaluate g at x minus 3. So this is going to be equal to, since g of x is equal to x plus 2 squared, this is going to equal, let's do some double parentheses, x minus 3, and then plus 2, and then this is all getting squared. And so dropping the inner set of parentheses, we can add the like terms minus 3 and 2, so that we have just x minus 1 in the parentheses now. And this is squared. And again, we could be happy with our answer here. Lumen would count that as correct, or we could FOIL this out, and we would have x squared minus 2x plus 1. All right, and for the 4th example, we want to find g composed with f evaluated at 3. So just like before, we could do this problem either way. We could use our work from the previous example to say, oh, we already know the rule of assignment for the composite g of f of x, and just use that to evaluate it at x equals 3. So if we're doing that, we would have, well, according to what we found in the previous example, 3 squared minus 2 times 3 plus 1, which is equal to 9 minus 6 plus 1, which is equal to 4. Or we could say G composed with F evaluated at 3 is equal to G evaluated at f of 3, whatever that is, and we'll figure out what f of 3 is. So f of 3 is equal to, well, 3 minus 3, which is equal to 0. And so g of f of 3 is equal to g of 0, which is equal to 0 plus 2 squared, which equals 2 squared, which equals 4. So again, either way, we found the same answer. All right. Okay, in the next two examples, we are asked to find functions f of x and g of x such that the given function can be expressed as the composite f of g of x. So we're going to be given some function h of x, and we want to find two functions f and g such that f composed with g of x is equal to h of x. So in our first example, we are given h of x equals x plus 1 cubed. And so here, since we're thinking that g is going to be the inner function, right? We're trying to write h of x as f of g of x. We can look at what we have in the parentheses here, since we have h of x equals x plus 1 cubed. And we can just take the expression x plus 1, and that can be the rule of assignment for g of x. And then for f of x, well, we can choose f of x equals x cubed. So if we take f of x equals x cubed, then we would have h of x is equal to f of x plus 1, since we're saying, okay, f of x is equal to x cubed. And then since we are letting g of x equal x plus 1, this is just equal to f of g of x. So we can have f of x equal to x cubed and g of x equal to x plus 1. Okay. For our next example, so we're still doing the same thing, except this time h of x is equal to the square root of x minus 1 over x plus 1. So since we have a square root here, how about we let f of x equal the square root of x? So f of x equals the square root of x. And so with this in mind, we can think of h of x as being equal to f of, and just looking at what we have under the square root here for h, f of x minus 1 over x plus 1. And so looking at what we have inside of f here, that's going to be what we want to make g of x. So trying to think how I want to organize this. So let's take g of x equal to x minus 1 over x plus 1. And so this gives us h of x equal to f of g of x, just like we desired. Okay, and that's it for 1.4.